In the last lecture, we studied Fraunhofer diffraction at single slit. In this lecture, we will study Fraunhofer diffraction at double slit. Let's see first the diagram. In this diagram, this W here is the plane wavefront whose wavelength is lambda. And there are two slits now, AB and CD. These are the two slits which are rectangular slits. And these two slits are parallel to each other. Width of each slit is equals to small a, and there is an opaque space between these two slits which is BC, and the width of that opaque space is small b. If that is the case, then the distance between center of slit AB to the center of slit CD is equals to A plus B. Now, when this plane wavefront incident on these two slits, as these two slits are parallel to each other, so at a same time, this plane wavefront will be incident on these two slits AB and CD. Then, according to Huygens principle, each and every point in the plane of both the slits acts as a secondary source and emit secondary waves in all directions. Let us consider secondary waves which are traveling normal to the plane of the slits. In this case, plane of the slits is perpendicular to this page. So, those secondary waves which are starting from center of each slit and they are traveling in a direction normal to the plane of the slits. These rays are brought to focus at point P0. This is the point P0. So at point P0, which secondary rays are reaching? Those secondary rays which are traveling from the center of each slit in a direction normal to the plane of the slits. They are reaching at point P0. And those secondary rays which are traveling in a direction theta with normal to the plane of the slit. So these secondary rays are making an angle theta with normal to the plane of the slit. They are brought to focus at point P1. So this is the point P1. So we are considering only 2 points on the screen, P0 and P1. Now what would be the intensity at point P0 and P1? Obviously, intensity at point P0 is the maximum, but that intensity would be or is because of both the effect, diffraction effect as well as interference effect. In the last lectures, we studied the difference between interference and diffraction. In case of interference, it is an interference between two wavefronts emitted from two coherent sources. So at point P0 and P1, the two wavefronts are emitted, one from slit AB and another from slit CD, and they are reaching at point P0 or P1. So there would be interference between these two wavefronts. But we also studied Fraunhofer diffraction from the single slit. So at point P0, there may be several secondary waves which are emitted from a single slit, AB or CD. They are reaching at point P0 and P1. And there is a diffraction, there would be an interference between these secondary waves which are emitted from the same wavefront. So at point P0 and P1, we will get some intensity, and that intensity would be combinations of interference and diffraction. So intensity is at point P1, as I said, is because of interference as well as diffraction. We already studied Fraunhofer diffraction at a single slit, where we got the resultant electric field ER, or the resultant amplitude, which is equals to Em sin alpha upon alpha. This is the resultant electric field because of diffraction from the single slit. In this case, the alpha is equals to pi by lambda a sin theta, where a is the width of the slit. Then let us assume that. Now we know that because of Fraunhofer diffraction at a single slit, we get this equation. So in this case, we are going to assume that there are two slits, and from each slit we get one wave in a particular direction whose amplitude is nothing but Em sin alpha upon alpha. So instead of going into how we get this Em sin alpha upon alpha, which we already studied, so we are going to assume here that from each slit we get one wave in a particular direction whose amplitude is Em sin alpha upon alpha. So amplitude of the wave is Em sin alpha upon alpha. We are assuming that from each slit we get a wave whose amplitude is Em sin alpha upon alpha in theta direction. In each direction we get one wave. But in the theta direction, let us assume that the amplitude of that wave is equals to Em sin alpha upon alpha. So those waves which are reaching at point P1, and now in this case we are considering only two waves. One from center of slit AB, another one is from center of slit CD. And these two waves which are reaching at point P1, and each wave is having amplitude Em sin alpha upon alpha. So two waves are reaching at point P1. So there would be interference between these two waves. And that interference, whether it is constructive or destructive, that will depend on the path difference between these two waves, which are reaching at point P1. So the path difference between the waves which are reaching at point P1 is, we can find by plotting a normal on this second wave, and the path difference would be this distance. So this is the path difference between the two waves which are reaching at point P1. And that path difference would be nothing but, as this is the theta, and the distance between center of each slit is equals to A plus B. The angle is theta. So this path difference, this is the path difference, and this path difference is equals to A plus B sine theta. So the path difference between the waves which are reaching at point P1 is nothing but A plus B sine theta is the path difference. Let us denote it by capital delta. If this is the case, if this is the path difference between the waves which are reaching at point P1, then corresponding phase difference. We know the relation between the path difference and the phase difference. So corresponding phase difference is then, let us denote it by small delta, which is equals to 2 pi by lambda A plus B sine theta. And let us assume that this is equals to 2 beta. This is what we are assuming, that the phase difference is 2 pi by lambda A plus B sine theta, which is equals to 2 beta. And therefore, the beta is equals to pi by lambda A plus B sine theta. It is similar like alpha. In case of Fraunhofer diffraction at a single slit, we assume that alpha is equals to pi by lambda A sine theta. In case of Fraunhofer diffraction at double slit, we are assuming that beta is equals to pi by lambda A plus B sine theta. Now, as you see in this diagram, at point P1, two waves are reaching. So what would be resultant amplitude at point P1? What we have to find is resultant amplitude at point P1. And to find the resultant amplitude at point P1, we are going to follow vector addition method. To find the resultant amplitude, we are using vector addition method. So let us first draw the diagram for this. This is the one wave emitted from one of the slit whose amplitude is Em sine alpha upon alpha. Then there is another wave which is emitted from the another slit, and amplitude of that wave is also equals to Em sine alpha upon alpha. And the angle, the phase difference between them, the phase difference between them is small delta. This is the small delta. That is the phase difference between these two waves. Now we have to find the resultant of these two. To find the resultant, what we have to do is join this, and this is our resultant, which is, let us say, equals to ER. So ER is resultant. So in this case, two sides of triangle represent amplitude from slit 1 and slit 2 of the waves, and the third side gives resultant amplitude ER. And we have to find this ER. Let us say that this point is O, this is H, or let us call it G, and this is H, OGH. This point is G. Then by vector addition method, we have to find the resultant amplitude, that is ER. To find that, which is, let's say, OH square is equals to OG square plus GH square plus 2OG into GH into cos delta. This OH is ER. So here we have ER square, which is equals to OG. This is OG. square of this. So we get Em square sine square alpha upon alpha square plus gh square, again Em square sine square alpha upon alpha square plus 2 Og into gh. So again Em square sine square alpha upon alpha square into cos delta. Let us take the common quantities. In this case, common is 2 Em square sine square alpha upon alpha square, then into bracket 1 plus cos delta. As you know that 1 plus cos delta is equals to 2 cos square delta by 2. So let us substitute this in above equation. Then we get ER square is equals to 4 Em square sine square alpha upon alpha square into cos square delta by 2. But this delta by 2 is equals to beta, because we assumed in the here we assume that the beta, this delta is equals to 2 beta. So beta, so delta by 2 is equals to beta. Let us substitute that. Then we get ER square is equals to 4 Em square sine square alpha upon alpha square into cos square beta. So this is nothing but resultant intensity. Let us find ER by taking the square root on both sides. So ER is equals to 2 Em sine alpha upon alpha into cos beta. And this is nothing but resultant amplitude. If this is the resultant amplitude, then what would be resultant intensity? Resultant intensity would be this IR is equals to 4 Em square sine square alpha upon alpha square into cos square beta. So that is the resultant intensity. Now see the equation carefully of the resultant intensity. So this resultant intensity, as you can see, has two components. The first component is Em square sine square alpha upon alpha square, and this is nothing but diffraction term due to single slit. This is diffraction term due to single slit. And the second component is cos square beta. Second component is cos square beta. And this cos square beta is nothing but is interference term due to two waves from two slits. So resultant and intensity consists two components. One is diffraction term and the another one is interference term. So let us see the diffraction term then. or we can say the diffraction effect. Now, diffraction effect gives central maxima at the center because we already studied diffraction due to single slit. So there is a diffraction effect, and this diffraction effect gives principal maxima at the center, and then we get alternate minima and secondary maxima of decreasing intensity on either side, as shown in this diagram here. This is the diffraction effect. These are the diffraction fringes due to single slit. So at the center of it, we get the principal maxima. Then on either side of it, we get principal, we get secondary maxima and the minimas. We get alternate here minima and secondary maximas. So that is because of diffraction effect. And this diffraction effect, as I said, there are minima, and the condition for minima is when alpha is equal to plus minus m pi. And you know that this alpha is nothing but pi by lambda a sine theta. And this pi cancels with this pi, and so we get a sine theta is equal to plus minus m lambda. So this is the condition for minima, where we get at this point, we get over here, we get minimas. And as you can see, exactly in between two minimas, there is a secondary maxima. And for secondary maxima, the condition is the alpha is equals to odd multiple of pi by 2. So it is, plus minus 3 pi by 2, 5 pi by 2, or you can say 2n plus 1 pi by 2. And that is equals to alpha. That is alpha. Where alpha is pi by lambda a sine theta. So in this case, this pi cancels with this, and what we get is a sine theta is equals to plus minus 2n plus 1 lambda by 2. So this is the condition for secondary maxima. So in the first graph over here, we get alternate minima and secondary maxima on either side of principal maxima. So that is diffraction effect. Then there is a interference effect. Now interference term is cos square beta. We got this term, the cos square beta. This is the interference terms. And this interference terms gives equidistant dark and bright fringes because it is an interference. In the interference, we get equidistant dark and bright fringes. Now, when we will get maximum intensity, that is when we will get constructive interference. What should be this cos square beta for constructive interference? That is maximum intensity. So this cos square beta should be 1 to get the constructive interference. And we will get cos square beta equals to 1. For that, the beta should be plus minus n pi, where n starts from 1, 2, 3, etc. Then we will get cos square beta. But you know the value of beta. So this beta, which is should be plus minus n pi, and that is equals to pi by lambda a plus b sine theta. So this pi here cancels with this pi, and what we get is a plus b sine theta is equals to plus minus n lambda. So this is the condition for constructive interference, that is the maximum intensity, and you can see here this one is cos square beta. This axis over here is cos square beta, and this axis in case of this is Em square sine square alpha upon alpha square, intensity axis. This is beta here, and this one is alpha. So we get the maximum intensity because of the interference, because of the constructive interference, whose condition is this: a plus b sine theta is equals to plus minus n lambda. Then when we will get the minimum intensity, that is destructive interference. For destructive interference, this cos square beta should be 0. And that is possible only when beta is equals to plus minus 2n plus 1 pi by 2. But as you know that beta is pi by lambda a plus b sine theta. So this pi here cancels with this pi, and you get a plus b sine theta is equals to plus minus 2n plus 1 lambda by 2. So this is the condition for destructive interference, or you can say for the minimum intensity. And as you can see, we get the fringes like this. We get equidistant dark and bright fringes. This one is bright fringe, this one is dark fringe. So alternate dark and bright fringes which are at equidistance. So the first graph is because of the diffraction effect, second graph is because of interference effect. And it's a combination of these two. The third graph over here is combination of interference and the diffraction effect. So what we get is, in the principal maxima, we can see the several dark and bright fringes. In principal maxima itself, we will see number of dark and bright fringes. Similarly, in the secondary maxima also, we can see alternate dark and bright fringes.